Hi everyone. So in this video we're going to go over some stoichiometry and stoichiometry related problems both on paper and also using Excel. So there's kind of a chicken and egg problem here. So I don't know if it's better to go through one part of the question using the paper and then type the formula into Excel, or if it's better to go through all of it on paper and then type all of it into Excel. But what I'm going to end up doing is going through the question on paper, and then I'll try to label things, and then we'll go over to Excel and we'll try to figure out how to punch these equations into Excel. Needless to say, in order to do this, and you'll have to do this fairly independently in future labs, including the very next lab, that you need to know how to both solve this problem and then take the solution and punch it into Excel. So these are the same types of questions you get in the general chemistry course, but the difference is here that you have 20 trials. So you don't want to be doing this calculation for empirical formula by hand 20 times. So it's really important we'll do it by hand once so you can see what it looks like, and then we'll switch and we'll put it into the Excel file over here in just a minute. All right, so that's basically what we're trying to accomplish in this video. So let's get right to it. So in all these cases, I'm going to go over the first set of data as the one that I do by paper, and then we'll punch it in here, and then I'll punch it in over here in Excel, and I will show you, basically how to pull it through for all the 20 trials. So let's take a look at the first one. It says an unknown compound containing carbon, hydrogen, and oxygen was decomposed, and we have the molar masses of those things. The masses of carbon and hydrogen were found for trials 1 through 20. Use the information to determine the average ratio of carbon to oxygen and hydrogen to oxygen. Comment on the precision and determine the empirical formula based on the average ratios. So this is basically our goal. So let's take a look here at how we might do this. So let's look at what we know. We know the mass of the sample, we know the mass of the carbon, the mass of the hydrogen, and we also know that this compound also contains oxygen. So it contains carbon, hydrogen, and oxygen. The first thing we don't know is the mass of the oxygen. So how are we going to find the mass of the oxygen? Well, the mass of the oxygen is going to be the mass of the sample minus the mass of the carbon minus the mass of the hydrogen. Said another way, if we take the total mass of the whole sample, and I need to move this over a bit, and we subtract out the mass of the sample, if we subtract from the mass of the sample, the mass of the carbon and the mass of the hydrogen, whatever's left has to be oxygen because that's the only other thing that there is. So in this case, I'm going to highlight this data so we can see it. We're going to take the first trial. So the mass of the sample is 5.1947 grams minus the mass of carbon, which is 3.1149 grams, minus the mass of the hydrogen, which is 0.7024 grams. So the total mass minus the mass of the things we know gives us the mass of the thing that we don't know. And in this case, the mass of the oxygen is 1.3774 grams. And as you probably know by now, I could simply type this in right here. If I wanted to, I could just type in 1.3774. I don't recommend you do that though. And the reason is, then you need to go do that for all of these, which wouldn't be bad if this is the only thing you had to do. But this isn't the only thing you have to do. You have to do all of that too. So I don't recommend doing it that way. It's better to plug it in as a formula, which we'll talk about in a little while. Now we want to find the empirical formula. We know the mass of, I'm going to highlight these again. We know the mass of the carbon, we know the mass of the hydrogen, and we now also know the mass of the oxygen. So if you remember, the empirical formula is the simplest ratio of moles. Well, in order to find a ratio of moles, we first have to find moles. So we need to find the moles of carbon, the moles of hydrogen, and the moles of oxygen. And I made a little bit of a mistake by going over that far. All right, so we know the mass of the carbon is right here. So if we take our 3.1149 1149 grams of carbon times 1 mole of carbon on the top over the molar mass of carbon, which is given right up here in the problem. Okay, or you could just look at a periodic table, which is 12.01 grams of carbon. Note that if you look at 3 different periodic tables, you'll get 3 slightly different masses. The difference is the sig figs of this. Now, they might be the same, but they might have different number of sig figs. So just keep in mind, if you want to get the exact answers that we have, you're going to need to use the exact molar masses that we have, and we try to give you those all along. Will it make much of a difference if you use 12.009.843 or whatever it is? Okay, I'm just making that up. I don't know what it is. No, it's not going to make much difference at all. But will it make a difference? Yeah, it'll make a slight difference. Okay, so just use our molar masses. All right, so we multiply by the top, we divide by the bottom to find moles, and we find that there are 0.2594 moles of carbon. Okay, so again, that tells us the moles of carbon right here. For hydrogen, we do the same thing. We're going to use the mass of hydrogen, which we already used before, but we're going to use it again. We're going to use 0.7024 grams of hydrogen times, for every 1 mole of hydrogen on the top, it's 1.01 grams of hydrogen. Of course, carbon and hydrogen have different molar masses, so in this case, we need to use the molar mass of the hydrogen over there. Okay, so it's 1.01, and when we do that math, and I apologize, this isn't lined up great. All right, so now we do this, multiply by 1, divide by 1.01, so it's going to be almost the same number, but not exactly the same number. We get 0.695 moles of hydrogen. Okay, so now this is the moles of hydrogen and the moles of carbon. We repeat for oxygen. So we found the mass of oxygen, the 1.3774 grams of oxygen. So we're going to put that in, 1.3774 grams of oxygen times, same thing, 16 grams of oxygen on the bottom, 1 mole of oxygen on the top. Again, we use a different molar mass for each of the things because they all have different molar masses. And when we do that, we get 0.08604 moles of oxygen. Now, we know that in a formula, we're trying to find an empirical formula, that the numbers are whole numbers. So this is effectively Cx Hy, O, Z, if you will. And what we're trying to find is X, Y, and Z, the subscripts for how many carbons, hydrogens, and oxygens are in the empirical formula. Well, we know these are whole numbers. If you want to find a whole number ratio of things, and you have a set of numbers, you want to divide them each by the smallest. So in this case, I want to divide by 0.08604. Why do you want to divide by the smallest? Well, the smallest divided by itself is, of course, 1, because any number divided by itself is 1. And the smallest on the bottom into the bigger one on the top is always going to be a number greater than 1. Said another way, you're going to get a whole number ratio. So I also want to divide this one by 0.08604. And when you do that, you get 3.013 as a ratio. And I want to divide this one by 0.08604. And when you do that one, you get 8.07 as a ratio. So this means for every 1 mole of oxygen, there are 3 moles of carbon and 8 moles of hydrogen. Said another way, based on this, we're going to use the averages to find the actual empirical formula. But based on this information, the formula of this is C3, because there are 3 carbons, H8, because there are 8 hydrogens, O1, we don't write the 1, because that's for 1 oxygen. So this is C3H8O. All right, now we need to translate this information into something that we can put into the Excel file that we can drag down. So the first thing I want to do is I want to find the mass of the oxygen. To find the mass of the oxygen, you'll recall, I subtracted the mass of the sample minus the mass of the carbon minus the mass of the hydrogen. So the mass of the sample is this one. So again, tell Excel to do math, you hit the equal sign. Then you click on the mass of the sample, which is in cell B3. Of course, you could just type B3 in there if you wanted to, minus the mass of carbon, which is in C3, minus the mass of the hydrogen, which is in D3. So this will give us the mass of the oxygen. And you'll notice it's the exact same number. Now, the reason you want to do it with a formula is you don't want to have to subtract all these numbers 20 times. And that's the reason we gave you 20 of them, so that way you have to do it by the formula, or you have to spend a really long time. Okay, so use the formulas. That's important. All right, we now want to find the moles of each of these things. So we want to find the moles of carbon, the moles of hydrogen, and the moles of oxygen. Well, for the moles of carbon, what we did was we took it and we multiplied it by 1 mole per 12.01 grams. Said another way, we divided by the molar mass. So we could take an equal sign that says do math, take the mass of carbon, and divide by the molar mass, 12.01. If you prefer, you could do equals the mass of carbon, I'm going to do it for this one, times 1 divided by 12.01. And now you'll see this looks a little bit more like this, okay? And if you do that, you'll get the same answer, all right? Because mathematically it's exactly the same. You're multiplying by 1 and then divided by 12.01, okay? Repeat for hydrogen. The only difference for hydrogen is we take the hydrogen and we divide by 1.01 because it has a different molar mass. And the only difference for oxygen is we take the oxygen and we divide by 16.00. You'll notice that if I go back into this formula, Excel dropped those 0 zeros. It just does that. Okay, that's just a thing that it does. So just be aware of that happens. Now, what I want you to notice is if we look at these numbers, okay, we have the moles of carbon here is 25.94. If we look over here, the moles of carbon is 25.9358868. Excel can do sig figs, okay, but the formula to do sig figs is about half a page long. All right, if you were to paste it into Microsoft Word, it'd be about half a page. We're not asking you to do sig figs here. Don't worry about the sig figs on these calculations because they're very difficult to do in Excel, okay? So don't worry. This is effectively the same number. And if we look here, 69544, 695, okay, 860. 4, this one actually comes out to slightly different, okay, slightly different than what we had in this case, and that may be a typo on my part. Yeah, it's actually 8609 that I had here, so all of these should be 9s. So I actually just couldn't even read my own handwriting on the examples. Okay, so these are all 8609, no big deal. All right, now you want to find the ratio of carbon to I'm going to take that equal sign out of there and just make this a little bit bigger so you can see it. Ratio of carbon to oxygen and ratio of hydrogen to oxygen. This is the mole ratio, so we want carbon on the top, and then we want to divide by oxygen on the bottom, and you'll notice it comes out to be about the same number. Okay, and then same for hydrogen. You want to take the hydrogen and you want to divide by the oxygen. And again, you'll notice it comes out to be the same number, just a different number of sig figs. Now here's the beauty of Excel. These things are all formulas. They're not just typed in numbers. So all I have to do is highlight all of these, grab this little box right here, and pull it all the way down to the bottom. All right. I have now done this for all 20 trials. It took me a minute to type them all in, all right, for the first trial, but then it took me no time at all to do it 20 times. That's the great advantage of Excel and why we would prefer you don't do this by hand. Now, can we stop you? No, but we would prefer that you don't do it by hand. So now I need to do the statistics. So you've seen this before, so equals average. And I'm going to take the values that I would like to average. Oops, my mouse is a little wonky, so it messed up a little bit on me there. So I type in the word equals average, and then I just highlight my data, and it takes the average. I now want to calculate the standard deviation, so equals STD EV. Okay, just make sure you're using this straight STDEV, not .p or anything like that. and then highlight your data, making sure not to highlight the average. Hit enter, and then the RSD, which is the standard deviation, which is right there, divided by the average times 1,000, because it's in parts per thousand. This should technically say PPT. All right, since these are ratios, they don't really have units. They don't have units, but this one still has a unit of parts per thousand. So you can see right there. Now, you could either type these in here, equals average, and then highlight these data, or you could simply highlight these and drag like that. Okay, and now you have it for the other data as well. So this is how we translate it from the piece of paper onto the Excel file. It's really important you practice with this, because you really are going to have a hard time if you don't understand how to do this, trying to calculate this 20 times. It's going to take you forever. Okay, so we don't want it to take you forever. We want you to learn how to use Excel so you can do it quickly. All right, so that is basically that. I'm going to pause the video and put a timestamp on, and then we'll be back. We'll go over number 2. All right, here we are on part 2. It says 12 groups of students reacted between 3 and 6 grams of salicylic acid, and it gives us a molar mass with excess acetic anhydride, automatically telling us that this is limiting reagent, and we can ignore this one. Each group measured their actual yield of aspirin, and then it gives a molar mass of aspirin. Determine each group's percent yield and the average percent yield on the class. Comment on the precision, which essentially means calculate the RSD. All right, so this is basically our goal. So here we take salicylic acid, we add acetic anhydride, and you'll notice that this acetyl group, this group here, is not here. It acetylates this, and what this effectively does is makes this a weaker acid. So this is as good of a painkiller, maybe better than this, but this is too acidic to eat regularly. Okay, give people ulcers. But this one, aspirin, as you know, people could take this every day. So this is basically that. I should give the disclaimer, I'm not a doctor, and that is not medical advice. I just think people do. I believe people do, but I don't know for sure. Anyway, the point here is we want to find the chemistry thing, the limiting reagent, and we already know that. And then we want to find the theoretical yield so that we can find the percent yield right here. So just like in the previous one, I'm going to do it on paper first. Then we'll transfer from the paper to the Excel file, and you got 12 trials. You don't want to do this 12 times, so let's use Excel to do it. So abbreviations, I'm going to call this one SA, just so I don't have to write out salicylic acid every time, and I'm going to call this one ASP, all right, for aspirin, okay, so that way I don't have to write it out every time. All right, so what I want to do here is, if I look at trial 1, I'm always going to use trial 1 here today. All right, so I have the mass of salicylic acid, okay, and then I have the actual yield, but the actual yield isn't useful for finding the theoretical yield. It's only useful for finding the percentage yield. So really all I care about here is the mass of salicylic acid. So by way of a plan of attack, okay, if you've seen my other videos, I use plans of attack. This is going to be grams of salicylic acid that I'm starting with. And at the end of the day, I want to find grams of aspirin that I am finishing with, because that is my theoretical yield, the theoretical yield of aspirin. So what do I want to convert to? Well, you've probably seen problems like this before. I want to convert from grams of salicylic acid to moles of salicylic acid. Once I have moles of salicylic acid, I can find moles of aspirin. And once I have moles of aspirin, I can find grams of aspirin. So grams to moles, I'm going to use a molar mass. Moles to grams, I'm going to use a molar mass. Moles of one thing to moles of another thing, always going to use a balanced chemical equation. So grams to moles and moles to grams, molar mass. I have molar masses. Moles to moles, balanced chemical equation. I have a balanced chemical equation. This is an organic equation. You may not have seen anything like this before. You may not know that there are carbons at each of these vertices, but that doesn't really matter here. It doesn't matter for 2 reasons. One, you already have the molar masses. You don't need to know how many carbons, hydrogens, and oxygens these things have. The other thing is that all you really care about it is that it's one of these, reacts with one of these to form one of these and one of these. Okay, so it's 1-to-1 stoichiometry, and moles to moles, we need the stoichiometry. Note that the 1 should not be written there. I'm just writing there for illustrative purposes. All right, let's take a look. We're using the very first trial, all right, which is 5.7694 grams of salicylic acid times, okay, we want to convert it to moles. Well, we're going to use the molar mass, and we're going to put the grams on the bottom. So I want to put the 138.122 grams of salicylic acid on the bottom, and 1 mole of the salicylic acid on the top. Now I want to convert from moles of salicylic acid to moles of aspirin. 1 salicylic acid gives me 1 aspirin. So I'm going to put 1 mole of salicylic acid, and I'm going to put on the top 1 mole of aspirin. Okay, times, I now want to convert from moles of aspirin to grams of aspirin. I'm going to again use the molar mass, this time of aspirin. I want to put the 1 mole of aspirin on the bottom because I want it to cancel out. And I'm going to put the 180.159 grams of aspirin on the top. And when I do all that math, I find that I can make 7.525 grams of aspirin. Okay, so this is the theoretical yield of aspirin. Much like before, I could type that in there, but that's probably not in my interest because then I would have to calculate it 12 times. I want to put a formula in there so I can just drag it. It's way easier. All right, now percent yield. So the percent yield is equal to the actual yield divided by the theoretical yield multiplied by 100. Okay, so it's the actual divided by the theoretical times 100. The percent yield in this case uses the actual yield, which is provided to you in the lab. You would actually measure this, right? You would take whatever aspirin you got and you put it on the balance, and that would be your actual yield. In this case, it's 6.8324 grams. And we're going to divide that by the theoretical yield, which is what we just found, 7.525 grams. And we're going to multiply that by 100 because it's a percentage. And when we do that, we get 90.79% yield. Okay, so this is our percentage yield. So this is how we're going to calculate these different things. Okay, so we found both the theoretical yield and the percentage yield. Now we need to translate what we did on a piece of paper into a formula in Excel. And I want to show you 2 different ways to do this first one. So the first thing you could do is you could take this equals this times, then I'm going to put it in parentheses, 1 divided by 138.122. Okay, so 1 over 138.122 times 1 over 1. Of course, you could leave that out because that is basically 1 divided by 1 is just 1. It's not doing anything. Times, parentheses, 180.159 divided by 1. Okay, so this is basically that. Now, do you need the parentheses? No, you definitely don't need the parentheses. That being said, I'm putting them there so you could see how this formula, where B28 is this, times 1 over, so I'm here, 1 over 138.122 times 1 over 1 times 180.1959 over 1. And then I could hit enter, and you'll notice I get 7.525 approximately grams of aspirin. Sig figs we talked about before. Don't worry about sig figs in Excel. It's a nightmare. Okay. How else could you do this? All right. Maybe you don't like that formula. Well, what did you effectively do here? You multiplied by 1, and then you divided by 138.122. Okay, you divided by this. Then you multiplied by 1 and divided by 1, that did nothing. And then you multiplied by 180.159, that's here. And then you divided by 1, that did nothing. And you'll notice you get the exact same answer. Okay, so whichever way you like to put the formula how you like. Okay, so this is kind of the simplified version. It's less typing, but it might be more confusing for some people. So use what you like. You're not going to get a different answer. And I should note, there's 5 other ways, or probably 100 other ways to put in the formula. And if you want to get really specific, there's an infinite number of other ways to do it. Just maybe no one would have thought of those ways. All right, anyway, percent yield. The percent yield is going to be equal to the actual yield divided by the theoretical yield times 100, and you'll notice we get that 90.79, which is the same answer that's right here. Just like before, once you got your formulas inserted, go ahead and drag. All right, so just highlight them, grab that little green box and pull it down. Good. Now your statistics equals average. Okay, select your data. All right, I selected from the bottom up that time instead of the top down, doesn't make any difference. Equals the standard deviation, STDEV. Note that I'm using STDEV straight. I'm not using some of these other versions of STDEV, all right, because you'll get slightly different answers, possibly. All right, we didn't test all of them. All right, make sure you're not selecting your average, okay, only of your data. Do you want the standard deviation? And then your RSD is going to be your standard deviation divided by your average, and we want it in parts per thousand, so we're going to multiply by 1,000, and we get 62.88%. Again, don't worry about sig figs. So this is how you can analyze this data based on a stoichiometry problem here, and now I very quickly analyze 12 pieces of data. Note that if I had 5,000 pieces of data, it would take me almost no more time because I could just drag it through for as many pieces of data as there are. We're giving you 12 to discourage you from trying to calculate all this by hand because that's a lot of work. All right, so in part 3, we have a solution stoichiometry problem. So we have calcium hydroxide reacting with hydrochloric acid to form calcium chloride and water. So it says a lab section of 11 groups of students, each neutralized calcium hydroxide with HCl solution. Given the mass of solid calcium hydroxide that each group dissolved to react, find the molarity of HCl solutions for each group, as well as the average molarity of HCl they were provided. Comment on the precision, which again means calculate the RSD. So this is basically very similar to the previous problem about aspirin, but now we have solutions, so it works a little bit differently. So let's look here what we're given. Well, if we look here for the molarity of HCl, I'm going to use trial 1, we're given the mass of calcium hydroxide. So we're starting with grams of CaOH 2. And at the end of the day, we want the molarity of HCl. And I'm writing it on the top because you'll see why in a second. Molarity is a little bit different because you can't exactly use dimensional analysis to get it. So what we want to do is we want to find the moles of hydrochloric acid. And then if you look here, we have the volume of hydrochloric acid. So if we have the moles over the liters, if we use the volume in liters, then we can find the molarity. So remember that molarity is moles per liter. So how are we going to do that? Well, we're going to convert from grams of calcium hydroxide to moles of calcium hydroxide, like we've done several times so far in this set. So grams to moles using a molar mass. Then we're going to find the moles of HCl. Once we find the moles of HCl, we're going to divide by the liters of HCl. And the moles per liter is the molarity. So you have to have both. All right, moles divided by liters gives us the molarity of the HCl. I don't know why I put a 2 in there. Okay, so that's basically that. So how are we going to do that? Well, starting with the grams, again, I'm using the first trial as usual, 0.2746 grams of CaOH 2 times. What are we going to use to convert to moles? We're going to use the molar mass, which is provided to us in the question, 74.09 grams of CaOH 2 per 1 mole of CaOH 2 times. Now we want to convert from moles of calcium hydroxide to moles of HCl. Balanced chemical equation. In this case, we have 1 mole of CaOH 2 per 2 moles of HCl, okay, because there's 2 HCl, times, we now need to divide by liters. This is not dimensional analysis. This is creating a new unit, in this case molarity. So we put a unitless 1 on the top. That moves the moles over. Then we put the liters on the bottom. Note, we can't put 28.57, which is the volume of HCl. What we need to put is the volume in liters, which in this case is 0.02857 liters. This is 28.57 divided by 1,000. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, repeat to the end. And when you do that, you get 0.2595, that's a 9, molar. Okay, like that. So 0.2595 molar. Now we need to put this formula into Excel. So equals means do math, as we've seen several times before. Take this, all right, then what do? We multiply by 1 divided by 74.09, or effectively we just divide by 74.09. Okay, multiply by 2, divide by 1, which effectively is multiply by 2, then divide by the volume in liters. This is a little bit tricky. So the volume in liters changes. So we don't want to just put in divide by 0.02857. All right, over here we have divide by 0.082857. What we want to divide by is this divided by 1,000. And the reason you want to do it that way is we want this to change every time. You'll notice we didn't use the same volume for each trial. So we want to take whatever volume we used and divide it by 1,000. And then whatever that volume is in liters, we want to divide everything else by that. Again, if you like, you can punch these in as whole things in parentheses. Without parentheses, it doesn't really matter because you're multiplying and dividing. But that's effectively how you can do it. All right, and when you do that, what you can see is that we get, with more sig figs, 0.2595. Conveniently, we click on that, we grab the little box. My mouse is a little bit messed up, so we just do and drag it down. All right, sometimes it clicks even though I don't actually click it. All right, and then we get the molarities of all of them. Then we can equal the average. We can grab the data, the standard deviation. As before, make sure you use just STDEV so it'll match what we have with what we have. Only select your data, don't select the average, and then the RSD is going to be equal to the standard deviation divided by the average, and it's in parts per thousand, so we want to multiply it by 1,000, and this gives us the RSD, which is commenting on the precision, if you will. So in this case, we were able to find the molarity of HCl in this reaction by using the provided data and just simply dragging through. Again, I just want to remind you, you want to make sure you don't plug in this number because this number is not static. Molar masses are static, okay? So we can just plug those directly in. 2/1 is static. It's always the same ratio. The mass changes with each trial, and the volume changes with each trial. So anything that changes with each trial needs to be plugged in as a formula or as a, cell location, or a cell location in this case divided by 1,000. It can't be plugged in directly. Otherwise, you're going to get the same answer every time. If you just plug this in and this, if you just plug this in and this in, all of these will come out to be 0.2595. All right, and you don't want that to happen. So that is basically how you would do this one. All right, so we've arrived at the last one. It says a lab section of 10 students each neutralize a sample of sulfuric acid with 0.2744 molar potassium hydroxide. Given the mass of sulfuric acid used and the volume of the potassium hydroxide each group used, find their calculated molar mass of sulfuric acid as well as the average determined molar mass. Comment on the precision and accuracy of the overall experiment, and then to find accuracy we have the accepted molar mass, which is going to be 98.079. All right, so this is basically a little bit different than what we've done in the past. So the molar mass of, in this case, sulfuric acid is going to be the grams divided by the moles. All right, molar mass is grams per mole. Normally you'd look it up, 2 H's, an S, and 4 O's from a periodic table, you can find the molar mass. But here we're asked to experimentally determine it. Well, if we look here, the mass of sulfuric acid is very easy to find. All right, so the grams are easy to find because they're given, right? 1.1965 grams for the first trial, and then for all the other trials you see there. If we look at the grams, we can find it. But what's not as easy to find is the moles of sulfuric acid. So what we need to use is the balanced chemical equation and the stoichiometry to find the moles. All right, so if we look here, all right, we have a volume of, whoops, I didn't mean to do that, a volume of KOH that we used, 14.35 milliliters, and a concentration. Said another way, we can convert from liters of KOH to moles of KOH, and then finally to moles of H2SO4. Once we have moles of H2SO4, we can take the grams of H2SO4 and we could divide by the moles, and grams per mole is molar mass. This is new. Moles to moles we've done several times before. Balanced chemical equation. I don't know why that keeps happening. Okay, the balanced chemical equation. For liters to moles, we need to use the molarity. So the first thing is we have to use the volume in liters. So divide by 1,000, 0.01435 liters of this KOH solution. We want to convert it to moles using the molarity, the 0.2744 molar. So what does that mean? It means there's 0.2744 moles of KOH per 1 liter of the KOH solution. This is the number of moles in a liter, because molarity is moles per liter. To convert from liters to moles, you use a molarity. Grams to moles of molar mass, moles of one thing to moles of another, balanced chemical equation. Those are the only 3 things you need to do in stoichiometry. All right, now we want to go from moles of KOH to moles of H2SO4. Moles of one thing to moles of a different thing, balanced chemical equation. So we got to put KOH on the bottom, so we put 2. 2 moles of KOH goes on the bottom, and on top 1 mole of H2SO4. Again, 2 KOH, so 2 on the bottom, 1 H2SO4, so 1 on the top. And when you do that math, you get 0.001696 moles of H2SO4. All right, now to find molar mass, it's grams divided by moles. Well, we know the moles, and we also know the grams. So we take the 0.1965 grams divided by the moles that we just found, 0.00161. I made a mistake here. This is 1969, not 1696. So it's 1969 divided by the 1001969 moles. And when you do that math, you end up with 99.81 grams per mole. All right, so we found the moles, and then we divide that. Now, this is a little bit tricky to plug in one cell, which is why it's last, okay? So the first thing you want to do is you want to take the mass, all right? And then you want to divide that by the moles. So I'm going to take the mass, and then I'm going to divide, because I want the mass on the top, by the moles. Well, the moles involves taking the volume and converting it into liters. Remember, we started with liters, not milliliters. So we took this and we converted it to liters. Parentheses here are definitely necessary for this whole thing. But do you need these intermediate parentheses? Probably not. Okay. Once you have the number of liters, you want to multiply by the molarity. That's right here. Okay. And then you want to take that and you want to divide all that by 2. All right, then I'm going to close that parenthesis. This whole thing has to be in parentheses because you want to figure out what this is and then divide into this. So it's not a dimensional analysis single line. It's all of this is on the bottom here, if you will. So you got to do all that first and then divide in. So you do need these, the black parentheses here. Okay, then you hit enter, and what you notice is you get the exact same answer, just with a whole bunch more sig figs. Now, this formula can be dragged. Oh man, my mouse is terrible. All right, so I'm going to hit Control Z a couple times. Ooh, it's being really a pain right now. All right, and then you can drag it through like that. So now we need, again, as you've done several times, the average of these values. Okay, the standard deviation. I forgot an equal sign. So just go back and put it in. All right, the standard deviation of these values, and then the RSD, which is the standard deviation, divided by the average, and we want it in parts per thousand, so we multiply it by 1,000. Now, the percent error is a little bit different. So the percent error is how much does, in this case, the average value deviate from the accepted value. So in this case, you want to use the function ABS because you want the absolute value of this number. You want to know how far these two numbers are apart as a percentage. You don't want to know which direction it is. Said another way, you don't want it to be plus or minus, so you use the absolute value of, in this case, we're going to use the average value minus 98.0779, the accepted value. Now, it doesn't matter if you take 98.079 minus the average, or if you take the average minus the 98.079, you'll get the same answer because you have the absolute value symbol here. Then you want to divide by the accepted value, 98.079, and this is a percentage. So it's the difference between the numbers divided by the accepted number times 100, 100, because it's a percentage, not 1,000. All right, so what is this doing? It's taking the absolute value of the average value minus the accepted value, taking that, dividing it by the accepted value, which is right here, and then because it's a percentage, we're simply multiplying by 100, and you can see that the percent error here is very small, and that's not very surprising. Look, this is 98.10 effectively, and this is 98.079. These two values are very close together, so the average value is close to the accepted value. I hope that you found this information helpful, and I really appreciate you watching this video. This stuff takes practice. It takes practice to be able to do this. It takes even more practice to be able to translate it here. Please use this opportunity to practice. For this particular lab, you can just copy the formulas that I put in here if you want. But when you get to the next one and the next one after that, you're going to pay the price if you do that. You need to understand how to get these numbers in here. And we learn by practicing and making mistakes and struggling through things. Okay, that's how you get through things. All right, thanks for watching. I really appreciate it. Have a great day.